Okay.
Okay, awesome. Okay, thank you for coming, Charlie. Please go ahead.
Okay. Thank you very much, Dana. First, for organizing this seminar series. I think recently our IFAS AI faculty working group, we formed two committees. One is a seminar committee, another one is a governance committee. The seminar committee is chaired by Dr. Daeun Choi. I think this committee has been working very effectively. Recently, we are developing the seminar schedule for the coming months. The governance committee is chaired by Dr. Charlie Messina. I want to thank all these, two committee members for working hard to advance our IFAS AI program. So today, let me first remove this. Okay, so the online audience, can you see my presentation mode, my slides in presentation mode? Everything's okay? Just want to confirm. Yeah.
Nothing is working.
Yeah, we have some technical difficulties today with our projectors, computers for in-person participants. Okay, I see. Okay, so I have chat. Okay, everything seems like working. So go ahead. Sorry, we have to switch the order because Haipeng's computer has some issue or cannot load his presentation. So I will first start. So today I'm very glad to share my research progress on developing automation and deep learning to advance plant phenomics and post-harvest handling. Okay, so I think we all understand the current challenges facing food and agricultural systems. The global population is increasing and is expected to be 9 billion by the middle of this century and 11 billion by the end of this century. To provide enough food, fiber, feed, and fuel to the growing population, we have to increase agriculture production by 70% or more, right, based on the UN projection. Meanwhile, we also face global climate change. As you can see from this map at the lower right corner, as the global temperature increases, crop yield will decrease by 30 to 40% in most areas with a higher temperature. Meanwhile, we also have this productivity gap. There's an index called TFP, total factor productivity, which measures the output versus input. Based on the UN projection, we need to have 1.75% growth rate of TFP in order to meet the growing demand by the middle of this century. But right now, this growing rate is only 1.5% for global average. And for developing countries, this rate is less than 1%. So we have a huge gap between where we need to be, 1.75%, and where we are now, which is much less. In addition, we also have a huge challenge in labor shortages, right? As the living standard increases, nowadays less and less people would like to work on a farm for repetitive work under a harsh environment. For example, this repetitive and harsh, farm operations and hard work includes harvesting of specialty crops, fruits, vegetables, weeding for some, crops, especially in organic production, and pruning, right? All those operations right now are kind of conducted or performed by human workers. So this is not a huge challenge. Based on a report from national academies, the report is called Science Breakthroughs by 2030. AI-enabled digital agriculture will play a very important role to transform the current agriculture and food production systems. So this slide shows the overall overview of my research program, and we focus on developing this AI-enabled digital agriculture, specifically automation technologies and machine learning data analytics. So we currently focus on two applications. One is plant phenomics to help breeding and genomics research. And the second area is overall crop production, precision agriculture, including post-harvest handling. So our hope is to develop this AI-enabled digital agriculture system to make our current food production more productive with less input of water, energy, chemicals, and labor, right? So we develop robotic systems that can be used for autonomous data collection for phenotyping purposes. The robotic system certainly can also be used for other applications, for example, weeding or certain chemical treatment of plants in the future. But right now we focus on high throughput phenotyping for autonomous data collection. Okay, so here you can see some of the ground robotic systems developed in our lab. I will give more details about some of these platforms. We also investigated a drone-based data collection systems in the past. My group also developed customized embedded sensors for agriculture food systems. So we collect a lot of data using these robotic systems equipped with the various sensors depending on the application purposes, right? And to make sense of this data, we need to develop machine learning methods and computer vision techniques to extract useful information from those data. Here I list some examples of my research group in developing computer vision and machine learning-based methods for phenomics and post-harvest handling. For example, we used multi-object tracking from video frames to detect and count number of seedlings to evaluate crop emergence rate and seedling vigor. We also monitor crop growth over time through 4D imaging, which is basically a registration of a 3D point cloud over time. We also used point cloud and deep learning, 3D deep learning for 3D architecture analysis of plants. We'll talk about that later. We also leveraged the object detection and instance semantic segmentation from RGB images for flowering time and fruit cluster trait analysis. And in addition to these normal regular imaging modalities, we also explored hyperspectral images for internal bruising of berry crops. So all those novel phenotypic traits, information and knowledge could be used to advance genomics and breeding programs, as well as in-field precision crop management, harvest decision-making, and post-harvest quality improvement and loss reduction. So first, let me talk about robotic system we developed for automated data collection and for high throughput phenotyping. So in our lab, we developed this modular agricultural robotic system, also called MARS, because currently most agricultural robots are single task based, right? So they can be used for example, planting or weeding. Our idea is to develop a modular agricultural robotic system that can perform multiple tasks with the flexibility to reconfigure the robot with the different modules, right? So one robot can be reused for different purposes. That will reduce the cost of the agricultural robotic system for growers. So we have hardware modules and software modules. Hardware modules have 8 different modules. As you can see, controller, wheel, frame, power, and connection. Those are mandatory modules. And the 3 optional modules, including actuation, smart attachment, and sensing. And the software modules have 3 components, 1 mandatory control module and 2 optional navigation and vision to increase the autonomy of the robotic system. So with this modular design, we can reconfigure the robotic system based on the application, based on the budget of growers or users. So as you can see from the lower left corner, we have 4 different configurations of this Mars with the different active wheels. For example, configuration 1 has 4 different active wheels. Actually, this is called a 4-wheel drive, 4-wheel steering, or articulated wheels with 8 motors. It has a lot of flexibility to be operated in the farm. And configuration 2 has only 1 active wheel. It's a tricycle configuration, right? But 2 passive wheels and 1 active wheel. Configuration 3 and 4 both have 4 active wheels, but these wheels are in skid steer configuration, and they have different width between wheels. We have 2 categories of Mars. One is called Mars Mini, another one is called Mars X. I will introduce later. Mars Mini is a light duty, and low-cost robotic platforms. Some of the components can be 3D printed to perform some light-duty tasks on the farm. And as you can see at the lower right corner, these 2 images show the implementation of Mars Mini for configuration 1 and 2, as I explained earlier. Okay, so before we implement the robot in the field, we first did some robot simulation in robot operating system, gazebo, simulation environment. So this is a Mars Mini. We tested it, tested our algorithms, navigation, and object detection, deep learning models in simulation environment to test the Mars Mini's performance in detecting the lines for visual guidance, as well as counting the plants. So as you can see, we have 2 cameras. The front view camera is for road detection and visual-based guidance, so we don't have to rely on GPS. And the camera facing downward basically detects plants. And we use multi-object tracking, deep learning, deep sort, this kind of framework to detect and count the number of seedlings, as well as weights. And at the lower right corner, we use the Visual SLAM to perform this 3D mapping of the field. Okay, so this is a simulation of Mars Mini. We present this work last year in ASCB conference. And the second category of Mars is we call it Mars X, which is a more heavy-duty platform. It's made of aluminum extrusions. And in this configuration, it has a 4-wheel drive, 4-wheel steering. It has all this power module, driving module, steering module, and the control modules. And we have tested this platform rigorously in terms of passing obstacles, traversing the field, climbing the slope. Overall, it performed well. And in the past couple of years, we have deployed this Mars X into different settings. Sorry, the noise is maybe loud. So this is well, you can hear the wind. Mars X deployed in Citra for blueberry yield estimation. We deployed 3 different cameras, top view, right view, and the left view to address occlusion issue. And a little bit noisy because of the wind. So we present the work in ASCB conference this past year. We are still further analyzing the data. Hopefully, we use the ULU to detect the barrier number and count the barrier number, and provide this information for breeders. Actually, we are collaborating with Dr. Minus in horticulture department. So this slide shows our current ongoing projects. On the left, we modified the Mars X, as you can see, to feature lower, shorter plants, in this case, peanut. And this project, we are collaborating with Dr. Tillman to estimate the yield of peanut crops in situ. And in this setup, we use RTK GPS for autonomous navigation. In the field, we collected imaging data of 120 plots, I think in August. We are analyzing data at this point using both object detection as well as a multi-object tracking approach for peanut pod detection and yield estimation. On the right, this is another robot we developed for plant pathologist and breeder in University of Georgia. It's called Watson. Watson is the name of a detective. In this case, we try to detect plant disease for peanuts. And this robot, as you can see, compared to Mars X, it only has 2 active wheels. So the cost would be lower. So this is a basically differential drive to robot. The 3rd wheel is just for supporting. It's a caster wheel. So currently this robot has been tested for 3 years, and we are still improving its reliability, and we are collecting phenotyping data for canopy disease and try to do stress phenotyping. Still work on progress. So next, I want to talk about deep learning methods we explore and develop to make sense of the imaging data we collected in the field. As I just showed a simulation, robot simulation, right, video, and we can detect seedlings using multi-object tracking. In this project, my students and we developed this multi-object tracking approach for flower detection and counting for cotton plants. Flower tracking is more challenging in seedlings because of occlusion, right? As you can see, flowers could be occluded by leaves, the dense foliage. There are also many flowers. So we modified a deep learning tracking model called the center track, as you can see on the upper left corner, by incorporating 2 different attention mechanism, channel attention and spatial attention, to improve the performance of this tracking approach for flower tracking. So the input of this center track model are 3 frames of images. The first, because this is the video frame input, we get the frame from the current frame T, and the previous frame from T-1, as well as the heat map of detected objects, the flowers in this case, in the previous frame. So those are 3 image frames input. And output of this center track framework include 4 different components. The heat map of the current frame, indicating where those objects, flowers are, the size and offset of all those detected objects, as well as the displacement of the same object between the previous frame and the current frame. So we can make association between frames, okay? So with this modified center track, we achieved average precision at 50% threshold of 0.9 for flower tracking for cotton plants. We present this work in 2021 ASABE conference, and this work received the ITSC conference paper award. So based on our experience, some flowers can only be seen from one view, but some flowers cannot be seen, because of the single view. So we try to address this occlusion issue by including 3 different views and use multiple view geometry to project different views into one single view. As you can see, we collected data, imaging data, video data from middle view, left view, and right view, as well as a depth image. So as you can see at the bottom, those are depth images of the flowers. So we first did the tracking of flowers independently from these 3 different views. And then we get the location of each identified tracked flowers, and get that depth information. And using both the, but all these three cameras are fully calibrated. And we know the depth, we know the position of the flower in the image, in each individual image. Based on triangulation, we can project the left and the right view to the center view. And then we did this cluster analysis. So we can basically combine all the tracking and detection from 3 views into a single view, and then get the more accurate count, okay? So we achieved R-squared value of 0.92 in terms of number of flowers, and mean relative error of 6%. So the result is pretty good. In addition to RGB images and video frames, my group is also actively investigating 3D point cloud data for phenotypic trait measurement. In this example, as you can see, we use the photogrammetry method to take multiple images around this cotton plot. As you can see, this is a high resolution 3D point cloud out of this photogrammetry method. And this colorful image next to the 3D point cloud representation, this is a supervoxels, okay? And we use supervoxels and a clustering algorithm, as well as machine learning methods to classify those supervoxels as cotton bolls or branches or background. And ultimately, we can detect and count the number of cotton bolls from this 3D point cloud data. We achieved 96% accuracy in this case. The 3D mapping can address the depth ambiguity and occlusion issue from 2D RGB images, right? So with the GPS and the spatial information, we can also map those cotton bolls in terms of their location, the relative position of those bolls to the main stalk, main stem, also to the branches, because the location of cotton bolls also can affect the quality of cotton fiber. So we can get not only the lump sum, the total number and the yield of cotton bolls, but also the location and spatial distribution of cotton bolls. And this will be very useful for plant cotton breeding and physiological studies. So the method I just introduced, we used a support vector machine, which is a traditional machine learning method. It requires handcrafted features. So recently, my group has been investigating this 3D deep learning approach that can learn those 3D point cloud features automatically. So in this case, we used a method called the point voxel convolutional neural network for a plant parts segmentation, semantic segmentation of cotton plants. So the workflow on the top shows the overall process. We get the input of a point cloud, with basically X, Y, Z coordinates of these points from cotton plant. And those 3D point clouds were acquired using LiDAR, okay, laser ranging sensor. And then we perform the pre-processing, including denoising, normalization, downsampling, to reduce the size of point cloud. And then we perform this semantic segmentation using PVCAN to classify the plants into 3 different classes: the main stem, branches, and bolls. And then after post-processing, we can derive architectural traits that are relevant to plant breeding and physiological studies. As you can see at the lower left corner, this is qualitative results, classification results using PVCAN of segmentation. As you can see, the red indicates the main stem, blue indicates the branches, and blue cotton bolls, and the green represent the branches. Overall, I think as you can see, qualitatively, the PVCAN performed well. Quantitatively, we achieved a mean intersection over union of 98% for 3 classes, and accuracy 96%, and inference time of less than 1 second. By leveraging those segmented plant parts, we can derive important architectural traits for cotton, including the main stem height, diameter, number of branches and branch diameter, the number of cotton bolls, and number of nodes. So for 3D point cloud data acquisition using LiDAR, it's LiDAR is a relatively expensive equipment, and the LiDAR's resolution is also limited to recover some very fine details of plants. For example, in this project, we are collaborating with plant breeders, Dr. Azias Akins at the University of Georgia. This project is funded by an IFAS project. So we try to derive the architectural traits of peanut plants and get these fine details such as peanut pegs and branches. The pegs are very thin kind of plant architecture traits. So this cannot be done by regular LiDAR scanning point cloud because the laser point cannot hit these very fine, small structures of peanut plants. So here we explored a deep learning-based and photogrammetry method-based 3D radiance field for peanut architecture analysis. We call it peanut NERF. NERF is a very well-known, as I mentioned, deep learning-based radiance field model developed in 2020. So in this case, we first captured RGB images 360 degrees around the plant, peanut plant. And then we did a preliminary photogrammetry 3D reconstruction, and then put this imaging data and the parameters of these points, X, Y, Z coordinates, as well as the pose of cameras into this neural radiance field model, which is a fully connected deep network with the input of 5 inputs, X, Y, Z of the coordinates, as well as pose 2 angles of the camera poses. The output of this neural radiance field model are RGB and volume density of the 3D scene, okay? So we can query of this neural radiance field to get the RGB radiance of any point, even a newer viewpoint that we didn't capture using our RGB cameras. And we can render 2D images in novel views. We can also sample of this 3D representation to get a high resolution 3D point cloud. So using both 2D and 3D, and we use the model called Frostum PVCN to perform architecture traits analysis, including part detection. In this case, we did some preliminary trait extraction. We did a segmentation for part, as well as detection of part in 3D. But right now, we are also exploring more challenging traits, such as pegs and the branching pattern using this peanut NERF model. Okay, so we present this model in CVPR workshop earlier this year. So next, I want to talk about a project we did several years ago to use 2D image instant segmentation for mechanical harvesting improvement advancement for blueberries. As we all know, currently most fresh market blueberries are harvested by hand because mechanical harvesting can create excessive bruising for fruit. So to advance mechanical harvesting for fresh market blueberries, we have to reduce bruising. We also have to improve the crop kind of architecture or fruit cluster traits to make them inducive for mechanical harvesting. So to make this blueberry fruit inducive for mechanical harvesting, fruit clusters should be loose instead of tight, because they can be easily shaked off from the bush. And maturity should be uniform instead of less uniform. We have to harvest multiple times, right? So to evaluate those traits for plant breeding programs, for blueberry breeding programs, we need to evaluate fruit cluster traits. As I mentioned, the number of fruit, the maturity of fruit, and the tightness of clusters. So in this project, we leveraged instant segmentation model, mask RCN, to segment individual berries and evaluate the maturity of each individual berry. And also we use the orientation invariant bounding box to evaluate the tightness of the cluster. We quantify all those parameters because in the past, plant breeders have been using, subjective evaluation, eyeballing those traits. Now we can quantify them, and the result correlate with the manual ground truth pretty well. And this work has been published in Horticulture Research a few years ago. So next, I want to talk about sensing and automation technologies for specialty crop post-harvest quality evaluation. As I just mentioned, mechanical harvesting can create excessive bruising for blueberries, and it is estimated that fruit bruising can cause around 10% of total economic loss for blueberry industry. So in this project, we try to develop a hyperspectral based imaging approach to non-destructively evaluate internal bruising, because this will be very helpful for plant breeding programs. They can evaluate whether this particular genotype and fruit are susceptible to internal bruising or not, right? And this can also be useful for blueberry growers and packers, because when they non-destructively evaluate the internal bruising, they can make informed decisions whether to ship this batch of fruit to overseas market if they have less bruising, or they can sell those berries locally if they have more bruising, right? To make an informed decision to maximize their profitability. So we developed this hyperspectral imaging approach using both reflectance mode, as you can see on the left, as well as transmittance mode, using near visible and near infrared hyperspectral imaging approach. And the hyperspectral image, as illustrated on the right, you can see it's a 3D imaging cube, right? X, Y represent a spatial dimension, and the third dimension represent the spectral dimension. Each pixel represent a spectrum. So we have published this work in journals. And this is the result, qualitative and also quantitative result of reflectance hyperspectral image. As you can see, on the left column is a near-infrared raw image, and the middle column shows the predictions using our machine learning model. The red pixels indicate the bruised area, tissues, and the green pixels represent the healthy tissues. Because the first row shows all the fully bruised berries, and the bottom row shows the control intact berries. So we achieved a pretty good accuracy in terms of internal bruising prediction. And all those images on the right shows the ground truth. After we slice the fruit in half, observe the internal discolored bruised area. So we compared what we predicted with the ground truth. The overall accuracy was 96%. So as I mentioned, the mechanical harvesting and packing process can create bruising for fruit. And the process in the past was kind of a black box. We don't know exactly what's the quantitative measure of internal bruising. To address this issue, my group developed a sensor called a berry impact recording device. We call it bird sensor, which, as you can see on the right side, this encapsulates multiple components, triaxial accelerometer to measure the mechanical impact, and the memory chip, battery, and the microcontroller. And everything is cast into silicon rubber to represent a small fruit. And we developed the 2 generations of bird sensor, as you can see at the lower right corner. And the latest generation has a similar size as a penny. And the diagram on the left shows the bird sensor was used to quantify mechanical impact for mechanical harvester of blueberries, as well as packing lines. And by using this information, we can improve the mechanical harvester and the packing lines. And in 2014, we were invited by South America Blueberry Grower Association to use our sensor to quantify mechanical impact in about 12 packing lines. So as you can see, we use our sensor. The sensor size is similar to some large-sized blueberries. And we also developed a mobile app, so we can use the mobile devices to configure the sensor and view the data. And currently, we developed new capabilities such as wireless recharging, wireless communication, and we also commercialize the sensor. So that's all for my presentation. In the end, I want to thank all my collaborators involved in those projects I presented today, including collaborators from UF, as well as collaborators from UGA, which is my previous institution, and research collaborators from other institutions. I also want to thank funding support from IFAS, a Specialty Crop Research Initiative, Data Science for Food Agriculture Systems, AFRI, as well as a couple of grants from NSF, and a seed grant from IFAS, Lift AI, and commodity groups. Last but not least, I want to thank my lab members, current students, as well as former students who have conducted those research I presented today. And those former students now have become faculty members in US, Canada, and China. Thank you very much for your time.
Do you have any questions?
That was very enlightening. I'm interested with the berry impact reporting device. If you considered actually tailoring the matrix that embeds the sensor to see the mechanical impact on that material in a way to actually mimic what would be the subtle composition of a blueberry fruit.
Okay, yeah, I think that's a very interesting point. Currently, we have not done that, as you said, to mimic the internal composition, right, with a real berry composition. But I think that's an interesting direction we will consider. Right now, we tend to cast all the electronic components into silicon rubber. The silicon rubber, the Young's modulus will be similar to fruit, so that we only consider the surface. But internally, we didn't consider blueberry composition, but we could consider in the future. Yeah, that's an interesting point. Thanks. Thank you.
So very nice on different diverse applications. So I like especially the blueberry part. Understanding different internal glues for fruit clusters. So in reality, there's usually multiple problems in the same kind of setting, right? So and it looks like you have different algorithms designed in terms of understanding different questions. So my question is there a way we can integrate all this algorithm together? Do you design one algorithm so we're able to answer multiple questions? Is that possible, or how do they actually integrate all this methods together into understanding the kind of nature of multiple questions?
Okay. Yeah, I think that's.
Can you repeat?
Oh, sorry. Okay, sorry. Yes. So the question from Dr. Liu is, so I showed different projects, but for different purposes, we develop different models, machine learning models to address different issues, such as fruit segmentation, 2D or 3D, or object detection. Do we have an approach to integrate all different models? Just a single model. So I think that's a very interesting question. That represents the current AI development, right? We talk about narrow AI, which is current, in the past. We all develop specific AI models for specific problems. But now the trend is to move towards artificial general intelligence, AGI. Actually, I worked with some collaborators. We published a paper on AGI for agricultural use, and I think that will represent the future. Right now the large language models represent, some sparks of AGR. It's not exactly AGR, but that's one step towards that direction. So with a large foundational models, we could maybe in the future achieve one model to do everything. Yeah.
Great.
Thanks.
Thank you.
Okay.
Yeah.
Thank you.
If you have more question, please reach out to Charlie. I'm sure he will be happy to answer all of them. Yeah. Okay, can you share the slide?
Yes.
Yeah, now we're going to the next speaker, Haipeng Yu. He's an assistant professor in the Department of Animal Science. He conducts research and teaching in artificial intelligence in animal omics sciences. His research interest focuses on integration of multi-omics data to address emerging challenges in animal agriculture using statistical modeling, machine learning, and computational methods.
Okay.
Not working? Yeah.
I will try. Oh,
There we go.
let's see whether it's empty. Okay.
Okay,
Yeah.
can you share?
Yeah.
I'm not sure.
I think I need to share the screen with.
Yeah.
So which screen? Second.
Maybe, yeah, maybe second, and
Okay.
then let's see.
Okay. Then I can enlarge. Okay.
Ah,
Good.
Oh, maybe,
Oh, it's
yeah,
other
the
one.
number one.
Yeah. Okay.
And then I think we need to
Yeah.
switch it a bit
Oh.
to, yeah,
Display setting.
swap presentation.
Okay.
Yeah,
Okay. I
there
see.
we go.
Okay. Okay, thank you, Dana, for the introduction. So my talk today is about the development of user-friendly open source software, computer vision tools for the precision livestock farming. So in specific today, I'm going to introduce two software tools from my group. And the first one is we already wrapped up, and the second one is the one we are currently developing. And so the software tool I'm going to introduce today is actually for the image analysis software for this precision livestock farming. The first one I'm going to talk about is Changying Animal CV, which is an open source cloud-based web application that is designed for object detection, segmentation, and 3D dimension visualization. And this project is led by my PhD student, Jin Wang. And here I want to give you guys some a bit about the background introduction about what is the precision livestock farming. So for precision livestock farming, it's you can consider it's an integrated system that we based on the real-time data collected from the sensor and information technology that can help us to obtain the optimized data-driven management decision. This can be used to improve the traditional livestock farming system. So computer vision is one of the sensor technology. It can provide non-intrusive and cost-efficient real-time data collection. So with this a real-time timely individualized data collection, it can be a promising tool to provide the timely individualized animal care, which can optimize our management decision within this system. So also there are many computer vision packages as Charlie introduced available in the public domain. But how to apply these packages to animal science data, it can be very challenging. So because it requires people to be able to pre-process and post-process your data, train and validate your data, your model, and also visualize and visualize your result. So with this kind of task, it requires the user to be able to have some certain programming and data analysis skill set. It also requires us to have some access to the computing resources. So in addition to this, with the growth of this precision livestock farming, it's actually caused increasing demand for training animal science students in this computer vision area. So against this background, so the objective of this project I'm present here is we are trying to develop an open source user-friendly web application that allows the user to using a web pages to upload your data and then perform this object detection, segmentation, 3D visualization, as well as like 2-dimension, 3-dimension morphological feature extraction. And here I will briefly introduce what's the architecture about the software we developed. So we use the R-Shiny packages. We created the like a general framework for this software. And in detail here, we have the server side and also the user interface. So for the user interface, it's actually a web pages that allows the user to upload and select what kind of analysis you want to perform. And then you can download the result from these web pages. And the server side, it can take the input from the user interface and then perform all the analysis using the like computing resources we assigned it to, and then return the result to the user interface side. So to perform this computer vision task I mentioned here, we also implement the mask CNN, which is the one Charlie introduced. It's a state-of-art Python package originally designed for object segmentation. And here, this package was first released in 2017. And to implement this to our current software, we have modified the whole package to make it compatible with the current TensorFlow. And we also modified the visualization for the bounding box to make it show up the minimum rotated bounding box to get the morphological feature of the detected animals. And in addition to this, we also include other 3 Python computer vision packages, OpenCV, Matplotlib, and Plotly, to achieve the computer vision task I just mentioned before. So by integrating this Python, these Python computer vision packages, and also the framework created using the R language, we were able to achieve currently we are implementing 2 computer vision modules in this software. The first one is the object detection and segmentation. As you can see here, we were able to detect the peak and color using the different colors. This is instant segmentation. And we will, okay. And we were able to get the detection using the bounding box. In addition to this, we also allow the user to actually upload the 3-dimension information. Specific here, this is the information it captured from the 3D camera. So with this information, we created this interactive 3-dimension plot to allow user to study what's the back surface structure of the animal. And we also return the morphological feature in the 3-dimension to the user. So after we develop this software, the next step is how to let user to directly use it without to setting up an environment, without to request any computing resources. So to achieve this, we deployed our software in the hypergator with an instance that includes 32 CPU processor, 8 GPUs, and 122 gigabyte RAM. So by deploying this software on the hypergator, we allow user to just access to their software across the world and uploading your data and perform their analysis, then download the result. So this is the overall architecture about this software. And here I just want to briefly show how is the workflow for this software. So as you can see, once user log into their web pages, they can start their software and then they can select which module they want to use. So for example, on the left, they are going to, if they select the object detection segmentation, then next step is we are going to ask user to upload their input and also specify some hyperparameters. So some parameters, for example, the model and also some additional parameters. And after that, the user will able to run the model, and then the model will run in the server side and then return the result that allows the user to download for their usage. And at the end here is just so. And on the right is for the 3D morphological feature extraction and also visualization. And here I just want to use a short video to show how this 2 module actually works. So as you can see here, user you can upload it a single 2-dimensional images. This guy has questions. And then they can select what is the pre-trained model. Currently, we include 9 pre-trained model based on our data in this software. And then if you click the run the computer vision model, it will send the data to Hypergator, and then Hypergator will process the result, and then the result will actually, I think it's running, yeah. Yeah, I think the result will show up on the right. Let me see whether it's right. Okay, yeah, it was swapped before. Yeah, so once they specify the parameter, and then you can click the run, then the result will show up on the right window. So as you can see on the right, it shows the detection and segmentation result with the confidence score. And below, we based on this detection segmentation, we also extracted some morphological feature. You can consider this as image-based phenotype. It includes the location and also morphological that user can use it for their further analysis. And here we also allow the user to download all this result to their local storage. So, and in the second module here, where I showed how to use this 3D dimensional visualization and extraction. Again, here, user uploaded the deep sea information capture using the 3D camera. And then guys selected what kind of the pre-trained model they want to use, and then specify other parameters. And with this, they can start running the model. And again, on the right, it will return the result from the Hypergator. As you can see, the first one is actually the deep sea image with the detection and segmentation. On the right, user can interactively visualize the 3D dimension plot. Here, you can study what the back surface is. And below, we return what is the 2-dimensional features, like length, weight, error, and also have the 3-dimensional features. So this is the small demonstration about how to using these 2 modules in this online software. So here I want to briefly talk about what kind of a morphological feature or image-based phenotype we return. Here we return the weight, the error. We also return the parameter related to the bounding force, which is related to the detection. And we also have the another this 3D morphological feature. For example, what is the height or average centered for the animal, as well as what is the volume for this animal. So one thing I want to highlight is, as I mentioned, here we are actually provide software for processing image. We are not doing the statistical analysis for people. So by providing this morphological feature, we let user to decide what's the next downstream analysis they want to do. For example, they can fit their morphological feature like weight, length into the predicted model to predict the growth trait, such as body weight, body condition score. They can also using this trait to fit the genomic evaluation model as image-based phenotype. And for their detection result, they can using this bounding box coordinate information to perform the tracking the location of the animal. So as I previously mentioned, in the current online software, we provided 9 pre-trained model. This is based on our data we collected from the pig and the cattle. So, but we did realize when people start using this software, this weight may not always apply to their customer data. For example, they may have different angle, different view, or they may even have different species. So this creates a limitation for our software. That's why to overcome this limitation, so we made all the software code as open source. We also provide comprehensive tutorials on the GitHub. So this is the table content for this tutorial. So with this tutorial, people were able to train and label, evaluate their customer data. And once they get their trained weight, they can plug into our Changying animal CV locally to perform the local inference. So by doing this, we anticipate this will maximize the capability of our software. So in conclude, in this project, we developed this open source cloud-based web application to allow user perform object detection, segmentation, and 3D dimensional visualization. So by through a simply through a web application. As I mentioned before, so we released the source code along with the comprehensive tutorial to allow users to annotate their data, train, evaluate their model, and then perform local inference using our Shiny Animal Seaway. And with this, we anticipate that this software will be able to advance the computer vision research and teaching in animal science community. So currently we submitted our paper for journal review, and we also released this paper as a preprint. You can access it from the archive. And here it shows our collaborator from UF, North Carolina, and also Virginia Tech. In the second part, I'm going to introduce another standalone open source graphical user interface that we are currently developing, which is Animal MF. It's an open source graphical user interface that is designed to extracting the animal image-based morphological feature automatically and efficiently. So in the first project, I introduced the Shiny Animal Seaway, which is actually web-based application that allows the user to upload the images to perform this various computer vision tasks. But in practice, for the animal, we commonly actually collect the image for animal 24 hours, 7 days. Because this is because the animal is different from plants. It's actually always moving and it changes. So if you want to capture the real-time information of the animal, you actually need to put the camera there and capture the all the image 24 hours, 7 days. So as a result, this will actually accumulate a large amount of the image data. So in this case, there is a big demand for a software tool that will able to automatically and efficiently process this large amount of images and then return the image-based extracted morphological feature for user for the downstream analysis. In addition to this, previously I introduced the modern computer vision model that uses mask Gaussian. But for this kind of model, you need to have the data to fine-tuning your model to make it be able to accurately detect and segment the object. So, but in addition to this, we can actually try some traditional computer vision method. For example, using the thresholding method. That's why with this motivation, in this software, the objective is to develop a standalone open source graphical user interface for automatically, efficiently process the large amount of image data and then extracting the 2-dimension, 3-dimension morphological feature using the various computer vision algorithms. So again, here I will still introduce the overall architecture for this software. And here we use the Python tkinter to create the overall framework for this standalone graphical user interface. It also includes the server and the user interface size. And for the server side, we implement 3 computer vision algorithms. The first one is the mask Gaussian. The second one is the UNet. In addition to this, we also implement our customized thresholding algorithm. This is based on the color differences in the traditional thresholding. So we have customized this thresholding to allow to detect the small region and the large region of the animal in the view. So by incorporating these various computer vision algorithms, we were able to extract the morphological feature. Specifically for each animal, we have multiple images. We were able to return the summary statistic of this morphological feature based on this multiple measurement for the same animal. And we also allow the user to actually visualize all these features they extracted for each animal. And here I just want to using another video demo to show how this standalone software works. So we will release the software on the GitHub, and then user can just clone or download the software to the local. And for example, here this is once you download the software into the local, you can activate the software just call the execute the file. And this window shows the like current like a window of this software. And here we implement three like computer vision algorithm. And for example, using the mask classing as example, we allow user to first specify where is your data storage. Here, user can just go to the very top directory with the, for example, here for the call, it has the call 1 to call 5, and within each call they have multiple like image data. So user just need to specify the top directory. And in the next step, user will need to select what is the pre-trained model. In this case, this is for the dairy cow pre-trained model. And below, user can specify how many images you want to process. You want to process each one, or you want to skip the interval. And what is the maximum file you want to process. So once user specify the parameter, it will start process everything in their terminal in this case. Here it shows how many images processed and how many left. And after it process the images, it will show up the summary statistic and also allow user to visualize the result. So I think once it's done, it will pop up the new window. And here in this new window, it will allow user to check what kind of like file you process, what the information you have. And the user can also select the file you want to visualize the result. For example, here we can select the HIT file. And then it will pop up like a web application to allow you to visualize what kind of result you process for each of the file. I think this is a demonstration for this animal MF. And after the visualize, we actually save everything into the local, and you can access to all this measurement, include the summary statistic and also the original measurement for each of this file. So I think this is the demonstration for this image processing software. And in summary, this software we are still currently actively developing, but based on our current result, our animal MF can automatically and efficiently extract the morphological features from the animal image data using the various computer vision algorithms. In the next step, we are going to finalize the implementation of the stress holding algorithm to the software, which allows the user to perform this stress holding without any without providing any image data to train your model. With this, wrap up my talk today, and I'm very happy to answer any question you may have. Yeah.
Any questions?
Actually,
Haipeng, very interesting work. I think this web app is really interesting. Because in my lab, we also try to develop web app for user internal rules implementation. So I'm just curious. So do you provide APIs for users to develop their customized applications?
No, actually, no. So we just provide the tutorial, then they can just follow the tutorial.
Okay.
So yeah, that's the challenge part.
Okay. Also, you showed the 3D contour. So how did you get the 3D? Because your input is just the RGB images, right?
So actually for the 3D information, so we use some like a camera sensor called Intel RealSense.
Oh,
Actually the depth camera, they can capture their their height information.
Okay.
So for the 3D visualization, we are not doing 3D reconstruction.
Okay.
We just let user to upload their 3D information they have. We can visualize and also extract information for users.
Okay.
Yeah.
Thanks.
So related to that, so how affordable are those 3D sensing cameras?
I think you mean the price or something?
Yeah, exactly, to get the input.
So I think it's not expensive. It's like around $300, and the quality is they are keeping improving their warning. It's actually get very good quality for animal side. Yeah.
But would they be suitable for plants?
Well, that's too small an object. Yeah, I know that we have more
Okay.
pictures,
Okay,
we have investigated those, but the resolution is not enough for our high resolution.
Yeah, it's for animal because we only care about the overall. For plants, I think they need to customize like a high quality camera.
Is there any question from Zoom audience? I don't hear any. So actually, I have one question.
Okay, sure.
So you're using the web application
Yes.
to analyze the data.
Yes.
Do you also recycle those data and then retrain, or
I
do you do
don't,
with
I
that
don't
data?
think we have currently, I don't think I have access to this data because
Oh.
it's everything is in the instance within the hypergator. So
Oh,
I
okay.
don't think, I think people may have concern, like if I share your data with you guys, are you guys to use it? That's why I haven't touched that part. So,
I see.
yeah, but I don't think I have access to that data. They probably will wipe out after each time they use it.
Okay, so I was just wondering if
Yeah,
you're actually retraining because maybe
Yeah.
it may help make it better.
Yes,
a lot of-
yes, I think if we have large data set, the model will be more and more generalized.
Yeah,
But that part, we think about it, but our concern is that people will, because for animal data is very sensitive. So
Mhm.
people are concerned whether I should share with other people or not.
I see.
That's why we haven't started that part, but maybe that's the future we should do, make the model.
Maybe, yeah, maybe you can make an option for
Yeah,
the
yeah.
user to choose, like,
Yes.
do you want to be
Yes.
included in the data set?
Yeah.
Yeah.
Thank you.
Thank you. And do you have any other question? Yes.
So if the
Yeah.
model you are training can predict the animal disease, like they are abnormal from the normal animal, they should.
So that's a different story. I think if you want to predict disease, you need to check in more animal continuously. It's like what Charlie showed. You need to do the tracking because the one I showed is actually for the detection segmentation based on the image base. It's a single time point. If you want to track the disease, that's actually the one we are actually currently working on. We're also using the YOLO V8 combined with the tracker, it's a deep sort. We're trying to tracking the animal to see what is their activity for this cow. For example, if it is sit a long time or laying down there for a long time, there may be something wrong with it. And alternatively, you can check in their surface structure to see how they breathe, what's the breath frequency. So this can tell you something about like a disease. So this is another aspect that we are working on.
A conceptual question. In the
Yeah.
example that you showed, the nicely separate images of the things.
Yes.
The real populations probably are much higher densities. So
Yeah.
do you solve that with different camera angles or?
So I think, yeah, that's the challenge. If you want your model to return you very good segmentation, your model must be very like generalized, robust. That's why I think we tried, if we change the angle, sometimes you didn't get very good accuracy, especially the light condition will be a big issue. That's why for my impression is when you want to apply to your experiment design study, you better fine tune with your own data. And that after experimental setting, you already can collect some like preliminary data, you fine tuning based on the current weight, and then it should be give you a good accuracy. Yeah. It's okay.
So, I'm just wondering, how is the basic use case?
Yeah.
I mean, you already have the model and it's available online and
Yes.
people can use the on web interface.
Yes.
So to be more on the application side,
Mhm.
so for the use case in the farm, so is there any kind of, you mentioned light would be one restriction factors to
Yes,
detect
yes.
the model. So is there any kind of resolution of the image, and also you mentioned all the 3D information is actually convert to CSV file and
Yes.
convert over, right? So all these data transmission and conversion to the web interface that the model runs.
Yes.
So how this pipeline has been considered. I know that right now it's just a model. So
Yes.
for the application phase, what's the further
You mean
vision?
the application for the farm or how?
Right, right.
I think because here the original purpose we developed this one is actually we want first like people try it, and then it's more like education and research purpose together. So in terms of like how to apply to the farm, I think they need to actually deploy their model in their local computer in the farm. So in that case, they can fine tuning the model based on their data. They can also make them more like automatically. Because even though we use it's reasonable like resources on Hypergator, but if there's more than 100 people use it, it will just crash. So that's why it's like a food demo, but I think for application in farm, they need to have their local class, like local computer to deploy the model and then customize it for what they really care about. Either disease or the counting or either like tracking, like weather feeding behavior, like this, yeah.
Great. Any other questions? Do you have any questions? No? Okay, so if we don't have Kevin, let's give him a big hand. Thank you. Thank you, Charlie. Yeah, sure.
Sure.
Yeah, so this will conclude our seminar today. The next one is October 28th and it will be Zoom. Thank you. Thank you. Can we close the Zoom?
Yeah, yeah, sure.
Can we both?
And